Okay, on this page we will take a look at the relationship between convergent sequences and sequences that are bounded. So Theorem 5 says that if a sequence converges, then it is bounded. It is bounded. So the basic idea of this is take this first statement. So a sub n converges. What does this mean? This means that the limit as n goes to infinity of a sub n exists. So let's just say it equals some number. I'm going to say L. And then parenthetically, i.e., that means it exists. So a sequence converges if its limit as n goes to infinity exists. In other words, it equals a finite real number. Let's call it L. Now, we just proved in an earlier video, in an earlier example from this section, that no matter what number you start with, call that number a sub n, that number is less than or equal to the absolute value of itself, and it is greater than or equal to the negative of the absolute value of itself. So right here, I just demonstrated a lower bound and an upper bound, which proves this theorem. Okay. But what's important to keep in mind is the other way around, the converse. So if your sequence is bounded, does the sequence converge? And that is not true. So important here is the fact that the converse, which would be something like bounded implies convergent, is not true in general. So a good counterexample of this would be the sequence a sub n equals, let's say, sequence a sub n where the general term is given by the sign of that index n. Such a sequence oscillates just like the graph of sine does, but it never hones in or approaches a specific real number. It always just oscillates forever. So this is a sequence that is clearly bounded. It's bounded above by 1 and bounded below by -1. Now, what I've done here actually for this sequence is I didn't just give the... There's lots of answers for the bounds, because 1 is an upper bound for a sine of n, but also 2 is an upper bound. If 1's an upper bound, then any number greater than 1 is also an upper bound. What I gave these bounds of 1 and -1, I gave the sort of best bounds, the bounds that most closely bind or bound or group or box or enclose the sequence. They are called the greatest lower bound, because here's another lower bound, but this -1 is larger than this lower bound of -12. So we found the greatest lower bound and the least upper bound. You do not actually need to find the greatest and the least of these two bounds. You just need to provide a bound. So it doesn't have to be the optimal bounds, so to speak. Okay, Theorem 6. Bounded monotonic sequences converge. So from Calc 1, you should have been exposed to this term monotonic. It simply means that it is doing one thing. It's either increasing or it's decreasing. It's not increasing and decreasing. such as this example here of sine. It's increasing, then it's decreasing, then it's increasing, then it's decreasing. Monotonic would be something like x squared for x greater than or equal to 0. So just the right half of it, that's increasing always. Or even x cubed for all x. The cubic does flatten out for a moment, but it never actually decreases. So no matter what two x values I pick, x1 being less than x2, f of x2 is always going to be greater than f of x1, so it's increasing. So if you can show that a sequence is increasing and it's bounded above, then it converges. And to whatever it converges to, that limit must be less than or equal to the bound that you found. So for instance, let's say, here's a picture to go along with this. If I have a sequence whose terms are doing something like this maybe. So here's an upper bound. But this sequence here, which I'll just call a sub n, the limit as n goes to infinity of a sub n does not equal m, because clearly there's this gap. None of these black dots are anywhere near this line. So this is what we mean when we say the limit of a sequence might not equal the bound that you found, but it is going to be less than or equal to that bound you found. This is where the idea of a least upper bound comes into play, because the limit of this sequence is the least upper bound of that sequence. Same thing goes for a sequence that is decreasing. If you have a sequence that's decreasing and you know that there is a lower bound, then it's going to eventually have to not hit it, or hits it. At the very least, it doesn't go past it. So the sequence would converge. All right, example 9, counterexamples. The assumptions of theorem 6, this bounded monotonic convergence theorem, they are important. If any assumption is removed, the conclusion may not hold. Give an example of a sequence which is, so option 1, we want a sequence that is bounded and divergent. So this would be the example that we already talked about, sine of n. This is a sequence that is bounded between -1 and 1, yet it does not converge. So, oops, let's go back here. So I'm going to just go ahead and say that this sequence here is always between -1 and 1, yet the limit as n goes to infinity of sine of n over n does not exist. So now let's find a sequence that is monotonic, so either always increasing or always decreasing, that diverges. So we could do a sub n equals n squared. Or let's do n cubed. Doesn't matter, but we'll just say n cubed. Well, this is clearly monotonic. We just talked about that a moment ago. Yet the limit as n goes to infinity of n cubed equals infinity, which is not a real number, therefore the limit doesn't exist, therefore the sequence diverges. Example 10, existence of a limit. Prove that a sub n equals the square root of n plus 1 minus square root of n converges, then determine the limit of a sub n. So if we want to prove that this sequence converges, then we could go about it by using this theorem 6. We could show that this sequence is monotone and that it's bounded either above or below, depending on whether this is an increasing or decreasing thing. Okay? So one way we could go about doing this is the following. I could consider two consecutive terms of the sequence. So consider 2 consecutive terms. Not just a specific 2, but a generic, any 2 adjacent terms of the sum, or excuse me, of the sequence. So we already know what a sub n is. That's the square root of n plus 1 minus the square root of n. But I'll take a look at its neighbor, the next term of the sequence, the n plus first term. This would be the square root of n plus 1 plus 1, so n plus 2, minus the square root of n plus 1. So now remember that a sequence is, let's say for example, increasing if a sub n plus 1 is greater than greater than or equal to a sub n, just a sub n. So is the next term in the sequence larger than the previous term? Yes or no? That will tell you whether it's increasing. Decreasing, we just would reverse the direction of that inequality. So what we can do here is just check it. Let's take a look at what is the value of a sub n plus 1 minus a sub n. So a sub n plus 1 is the square root of n plus 2 minus the square root of n plus 1 minus a sub n. So this would be square root of n plus 1 minus the square root of n. So square root of n plus 2 minus the square root of n plus 1 minus another copy of that. So we really have 2 copies of that. Plus the square root of n. Now this one's a little bit tricky to tell. Is this greater than or equal to 0? If this is greater than 0, then we would have increasing. If this were less than or equal to 0, we would have decreasing. You can just subtract the one term over to see why that would be the case. So it's not clear by looking at this whether or not this is greater than or equal to 0. You could probably make some arguments, but it's not abundantly and obviously clear if this should be positive or negative. So sometimes you will encounter that. So the first thing I would do is check to see, try this route, because this is usually pretty straightforward. If that doesn't work, what you can do is a few other things. One other thing you could do is, again, pass to a continuous analog. And then, now that's continuous, there's a hope of it being differentiable, so you can take the derivative of this. So now, looking at this, you can wonder if this is going to be positive or negative. So what I could do here is notice that notice that this denominator here is larger than this denominator here. That means that this fraction is less than or equal to this fraction. Bigger denominator means smaller fraction. So then you can subtract them in the order that you want. So I'll subtract this term over to the other side. So clearly this is negative. So this is decreasing. Remember, a function is decreasing if its derivative is negative. That's one way to check. Another option that we can arrive at the same conclusion is something that's pretty hyper-specific to the question that we have. So this is why I didn't want to do this first or second, but I'll leave it for last because it sort of depends on the algebraic structure of this. But you could, for instance, in this case, because we've got square roots, we could sort of multiply by a conjugate, sort of what you did with limits in Calc 1. I could multiply this expression by a fraction, which is the conjugate of that first expression over itself. So the bottom just stays this square root of n plus 1 plus square root of n, but I'll FOIL the numerator and get n plus 1 minus n. N's will cancel, and we'll have this. So this sequence term is exactly the same as this sequence term. They look very different, but they are equal. So clearly this shows us that the top isn't changing in size, but the bottom is getting bigger. Well, if a fraction has a denominator that gets larger, then that means, as a trend, it's decreasing. So this also gives us decreasing, just through a different route. Another thing that this method does show us is that clearly this sequence is bounded above by the number 1. Because if I start with the number 1 and then divide it by some positive number, the result is always necessarily less than or equal to 1. Furthermore, this a sub n is going to be bounded below by 0. Because no matter how large we make this denominator, while that will make the fraction small, it will never make it exactly equal to 0. So this general term for the sequence a sub n is bounded between 0 and 1. So we have just shown that this sequence, whose general term is given by this expression, is both decreasing, therefore monotone, and it's bounded. So by this theorem, a sub n converges because it is monotone and bounded. So this theorem 6, bonded monotone sequences converge, that's how we get that convergence.